In this chapter, we are learning to think about molecules three-dimensionally. And that's really important because molecules are three-dimensional things. So here's a molecule right here. What we've learned in the past is that molecules like this, with just single bonds everywhere, have free rotation. So this atom can spin around there. This center bond right here can also move. So the molecule has rotation around there. And that's where I'll start talking about the packet. The first page of the packet says, as far as analyzing conformations of organic molecules, we must be able to imagine molecules three-dimensionally to study organic chemistry. And conformations, that's kind of a new word, are different arrangements of atoms that are interconverted by rotations around single bonds. So two separate three-dimensional structures of the same molecule are two different conformations. So what we have here is this molecule that I was holding here, but in a two-dimensional format that we can put on paper or on a board. But this molecule here is the same as this. I have P for the pink and B for the blue atom, and I'm going to bring this to the screen here. So we see the hashed bond up there for this first position is to this blue atom. It's going back while the green is coming out at you with the wedge. So that's how we show the three-dimensional molecule in a 2D format on the board. And this unit is about conformations. Well, this is one conformation of this molecule. And in this conformation, we have the pink atom coming out here and the blue atom coming out here. So they're both wedges in the molecule here. But we can also rotate 180 degrees like this to demonstrate an additional conformation. So in this conformation, now both of the pink groups are on the same side, so they would both be wedges. The blue atoms are coming back, so they'd both be dashes. And now the CH3s are in the same plane like they are here, but now it's going to be rotated down. So that's what we're going to draw now, is when we took this molecule and rotated it 180 degrees, we did that rotation around this sigma bond here. So with that 180 degree rotation, now both of the CH3s are here. This one we didn't move at all, but this one came 180 degrees down. Then we'll just add the wedges and the dashes in. So in this case, when we rotate it down, this pink one is still a wedge. And when we consult our molecule, our model, we started here. When we rotate it down, now the pinks are on the same side. They're both in front. So we have both the pinks in front, and the blues are now both in the back. So they're both the wedges. So these are conformers. They're two different conformations of the same molecule that just occurred by a 180 degree rotation. So it turns out that Newman projections are an additional way to draw molecules and show their three-dimensional structure. And that's what we're going to do in the next component here. I'm going to put something on the board and then I'll be right back. We're back. So skeletal structures are one way to draw conformations. And we saw that we have one conformation like this and we rotate it around and the second conformation looked like that. But Newman projections are even a more common way of looking at molecules three-dimensionally and trying to understand the stability of the different conformations that are present. So what happens in a Newman projection? So on your notes page, there's a little man that looks like they are looking right at the molecule here. And I'm not a great artist, so instead of a man, I'm just drawing an eyeball. So this eyeball is in the plane of the board, and it is looking directly down this carbon-carbon bond. So what is that going to look like? So I can actually kind of show you that with the molecule here. So the little man was looking at the molecule from this direction. So it was like kind of like my face looking at it like that. So the way that I can show you what that looks like is if I turn this toward the camera. So this is what, oh geez, it's so hard to do it. There we go. This is what that person would see. So how are we going to draw that on the actual board? So what we do is we to draw a Newman projection. So I'm doing this symbol to show that this molecule is going to be the exact same thing that's represented over here. And when I look down that bond, the thing that's coming directly down, so the thing that's closest to my chin is that CH3. So I'm going to start out by drawing this carbon atom. So this carbon atom here is this dot. And the CH3 is down towards my chin on that dot. What about where is the pink bond? The pink bond is out to the right of my head. So it's something like this. So the pink bond is out there. What about the blue bond? The blue bond is going this direction. Okay, so now we have a little bit of a challenge because we've drawn everything that is in the front here, but now we have to draw what's in the back. So how do we do that? Well, Newman projections have like a little circle around here. And that circle is supposed to indicate that there's a bond there. So that circle is the bond between these two carbon atoms. And if we think about where the other atoms should be, well, this CH3 is really close to my forehead, so it's going to be near the top of the molecule. Then the pink is, again, going into the board, so it's going to be on my left side. And then the blue is on the other side. So that would be a Newman projection of this molecule. And I want to let you guys look at the atom themselves here again. So this was the skeletal structure, and what we did is we turned it like this. It's like this. It's so hard on the camera. Goodness gracious. Why is this so hard? There we go. We turned it like that. So we saw that the pink was coming out to this side, the blue is coming out that way, the CH3 was going down, just like it shows right here. So what you should really do is, now that I'm holding this model where you can see what the Newman projection would look like, you should pause it and make sure that you can understand that this Newman projection, that the actual molecule looks like what you would expect from the Newman projection that is on the board here. So this is a Newman projection of this skeletal conformation. And what we see is that each group is staggered from all the other groups. So this bond is staggered from that bond. And this is actually called a staggered Newman projection. There is a distance between these. And the distance between the P to the B or the B to the CH3 is actually 60 degrees. So there's a 60-degree angle between those different substituents. And that's why we call it a staggered conformation. So what about this one? This one, again, remember, we took the molecule and we rotated 180 degrees around to make it look like this. So this is what that looked like. And again, what we're doing now for the Newman projection is we are taking the molecule and looking down that bond there. And what you can already see just from the model that I'm holding is that this CH3 back here is directly behind this CH3 in the front. This blue atom here is directly behind this blue atom in the front, and this pink atom is directly behind the pink atom in the front. So what would that look like when the eyeball looks down that angle? So we're going to draw our carbon for the first atom. And you could even stop at this point to try and draw this out. You're going to get more practice, so you might not need to practice right here, but you might want to. It might be interesting to see if you could come up with what the Newman projection should look like. But we have the CH3 down with my chin. And then the pink's there, blue's over here. And now this CH3 is directly behind that CH3. So the way that we draw it is we try to indicate that. We can't draw them right behind each other because then you couldn't see it, right? So we're doing as well as we can. This pink here, this other one is directly behind it, and the B is directly behind the B. So when we think about something like a lunar eclipse, what happens? Well, a lunar eclipse is when the sun, it's when the Earth is eclipsing the moon, okay? That's what a lunar eclipse is. This is not an astronomy class, though. But we call this the eclipsed conformation because this blue ball is being eclipsed by this blue ball. This pink is being eclipsed by this pink, and this CH3 group is being eclipsed by this CH3 group. So because of that, we call this the eclipsed conformation. And in the eclipse conformation, there is a 0-degree angle between those two CH3 groups. There's a 0-degree angle between those two pink groups. Versus in the staggered, again, it's a 60-degree angle between all of those different groups. So I'm going to be back with you again in a moment, but make sure you can understand how we took these skeletal structures and converted them into the Newman projections. To finish up our introduction to conformations, we now know what a staggered conformation is versus an eclipsed conformation. So ask yourself this question: which conformation would you expect to be more stable, the eclipsed conformation or the staggered conformation? So think about, forces, electrons. Do we want electrons close together, far apart? Think about those ideas and pause the video for a second and decide for yourself, eclipsed or staggered. Now unpause the video. Okay, nice job. And what I think that most of you probably selected is the more stable conformation is the staggered conformation. So the staggered conformation is more stable. And why is that? Well, the staggered conformation has no torsional strain. Well, what is torsional strain? Torsional strain is repulsive destabilization. Repulsive destabilization between electrons in the same plane. Between electrons in the same plane. So here there are no electrons in the same plane. The electrons in this bond are staggered from the electrons in this bond. Here, these electrons are eclipsing with these electrons, meaning they're in the same plane, meaning that there is torsional strain between the two covalent bonds here, the two covalent bonds here, and the two covalent bonds there. So all of those are torsional interactions. So because of that, the eclipse conformation has torsional strain, which makes it less stable. The staggered conformation has no torsional interactions. So which conformation would you expect to be more stable? The staggered one is going to be the more stable conformation. The last thing that I'll mention is I said that this is a 60-degree angle, this is a 60-degree angle, and what is that angle between? Well, in this first one we said it's between the P and the B. That's actually between this bond right here and this bond right here. So that 60-degree angle is between those bonds. So what is that actually called? We've given it a name, and it's called a dihedral angle. So that's the angle between two bonds on adjacent atoms. So the angle between two bonds on adjacent atoms. So this atom is adjacent to this atom, and this bond is on that atom, this bond is on this atom. So that 60-degree angle is called a dihedral angle. So a staggered conformation has all 60-degree dihedral angles, whereas the eclipsed conformation has 0-degree dihedral angles between those groups right there. So where does this go? Well, we said that this is less stable than this, and on the next page of the handout that you're working through, we examine the energetics of ethane conformations using Newman projections. So in the top left of page 2, we have the eclipsed ethane molecule in the skeletal structure, and in the bottom of that part we have the staggered ethane. They're both labeled. And staggered ethane is going to have none of those torsional interactions, so it's going to be more stable, versus the eclipsed ethane has all of those torsional interactions between each of the electrons that are in the same plane. So as we rotate through that molecule, every time we rotate, if when we rotated from here to here, we went down in energy. So ethane went from higher energy when it's eclipsed to lower energy when it's staggered. And if you just keep rotating, that goes back and forth, back and forth. And essentially, every time that graph went from up to down to up to down, when it goes from up to down, that first one is a 30-degree rotation. Then when you rotate 30 degrees more, it goes into the eclipse conformation. Then another 30-degree rotation goes down to a staggered conformation, and so on. And what we're going to do in the next video is look at the conformations of butane, a little bit larger of a molecule compared to ethane, and do that same energetics analysis. So I will see you then.